Hello students, in this video we'll solve a problem from the Lower Michigan Math Competition which involves two sums being equal where they have very different terms in the integer floor function. Let's prove that the floor of 2025 over the square root of 1 plus the floor of 2025 over the square root of 2 plus the floor of 2025 over the square root of 3. We keep going all the way down to the floor of 2025 over the square root of 2025 squared is equal to, prove that this is equal to, the floor of 2025 squared over 1 squared plus the floor of 2025 squared over 2 squared plus the floor of 2025 over 3 squared, squared of course, all the way down to what? All the way down to the floor of 2025 squared over 2025 squared. Like that. Okay? Great. Now this is going to be an absolute mess if we want to just try to approximate this thing over here. The actual numerical value, I don't even know what it is, right? I don't need to think about this, right? What's the key fact of this problem? The key fact of this problem is that there's how many terms over here? There's 2025 squared terms over here in this expression. And there's how many here? And there's just 2025 over here. Terms over here, okay? Great. What we're going to prove this in more generality, actually. So what we're going to do is we're going to say, in fact, what form does this have? This has the form, this problem has the form. And this is an illustration of proving a problem in greater generality. It's going to be easier in greater generality than trying to think about these numbers than it would be to actually prove it with these numbers, right? Has the form, the sum, k goes from 1 up to n squared. There's n squared terms over here. Then what do we have? We have n, the floor of n, over what? Over the square root of k, right? That's what we have over there, is equal to the sum, k goes from 1 up to n, of the floor of what? Of the floor of n squared over k squared. N squared over k squared, like that. Okay, so I would like to prove this identity, right? So I claim this identity. Claim this is an identity. It holds for any value of n. Now, how do we see something like that? Well, the idea is to double count, right? So what we're going to do is we're going to double count in the following way. So consider the collection of all ordered pairs. All ordered pairs A and B and N2. Such that what? Such that A times B squared is less than or equal to N squared. And we're going to parameterize omega. We're going to compute the cardinality of omega in two different ways, right? So note, we can parameterize omega by the following. We can parameterize it by j, a equals j, right? So if a equals j, what do I know? Then I know that this implies that j times b squared is less than or equal to n squared. And what does that tell me? That tells me that j is less than or equal to, or b is less than or equal to what? B is going to be less than or equal to, so b is less than or equal to, not j, but b is, right? B squared is less than or equal to n squared over j, and therefore b is less than or equal to what? B is less than or equal to the floor of n over what? The floor of n over the square root of j. Good. And so that tells me, what can I do? So j is less than or equal to what? J is less than or equal to n squared, right? This is true for j less than or equal to n squared, okay? So in other words, the cardinality of omega is given by that first formula, right? And now parameterize by k, parameterize omega by b equals k, okay? This implies that a times k squared is less than or equal to n squared, right? And that implies that a is less than or equal to the floor of what? A is less than or equal to the floor of n squared over k squared, okay? n squared over k squared. How many terms are there over here? Then a is bounded by what? A is bounded by n, right? So over here, k is less than or equal to n. And so now what do we have? So now I have the cardinality of omega. I've written it two ways. It's just the what? It's just the sum. The first sum over here, j goes from 1 to n squared, of what? Of the floor of n over the square root of j. That's also equal to this parameterization of it. The sum, k, goes from 1 up to n, of what? Of the floor of n squared over k squared. So we've just counted the cardinality two ways, counting the cardinality two ways. Gives us the answer, right? So in other words, I had a general statement over here, and I was just basically counting a collection of points that satisfy a certain bound, right? And that can be counted either horizontally or it can be counted vertically, right? And the exact dimensions, this will work for any sort of combination, right? I can consider all of these things over here for like an a cubed b squared. You get all sorts of different results of this kin using a technique like this. Thank you very much.